Okay, 4.4, Intro to Trig Equations, Part 2. For each angle, let's do a little startup. For each angle given below, state the principal angle as an exact value. Well, we'll have to define what principal angle is. Write an expression for all angles coterminal with each angle using the principal angle. What is this form called? This is called general form. Principal angle is the smallest positive, that's the key, smallest positive rotation angle with the same terminal arm. And I'll say with the same terminal arm as all coterminal angles. So if you look at all the possible coterminal angles, you'll write it in general form. It's the smallest positive rotation angle within that set. Okay, 5 pi over 4. The smallest positive rotation angle with the same terminal arm as all the coterminal angles. So this one, if I add 2 pi or I subtract 2 pi, if I add 2 pi, the positive angle is too big, right? So if I subtract 2 pi, then that's going to make it a negative coterminal angle. So this is our principal angle. So no need to rewrite it. Principal angle is 5 pi over 4. And then the coterminal angle in general form is 5 pi over 4 plus 2 pi n, where n is an element of all integers. Okay, negative pi over 6. Negative pi over 6, this is not the smallest positive rotation angle, right? So if I add 2 pi, that's going to get me my smallest rotational angle. So add 2 pi, or the trick is add a version of it with 6 as my denominator. So that's 12 pi over 6, and that's 11 pi over 6. So my principal angle is 11 pi over 6. And then in general terms, 11 pi over 6 plus 2 pi n, where n is an element of all integers, 540 degrees. It's positive, but is it the smallest positive rotational angle? No. Well, I can subtract 360 degrees and I get 180 degrees. If I subtract 360 again, I go into a negative coterminal angle. So my principal angle is 180 degrees. And when I write my coterminal angle in general form, it's 180 degrees. So 180 degrees plus 360 degrees n, where n is an element of all integers. Number 2, another startup warm-up problem here. The following solution contains one or more errors. Identify the errors and correct them. Solve tangent squared of theta minus 3 tangent of theta in the domain 0 to 2 pi. Round to 2 decimals. So I'm looking at this work. Tangent squared minus 3. Okay, well, that's good. Looks like we added 3 tangent to both sides, and then we divided both sides by tangent. So there's an error right there. When dividing by tangent of theta, you eliminate a possible solution. So be careful there. Okay, so you eliminate a possible solution. Because you're eliminating one of the factors, okay? And then that error is going to carry through. All right, so in fact, that's one of the solutions, 1.25 radians. Let's do the problem for real and correct that error. So I have tangent squared of theta minus 3 tangent of theta equals 0. I'm going to factor out a tangent of theta. So that leaves me with tangent of theta minus 3 equals 0. And I'm going to solve this like I solve quadratic equations, where I set each side equal to 0, or each factor to 0. Tangent of theta equals 0, and tangent of theta minus 3 equals 0. I find the reference angle first, so the inverse tangent of the absolute value of 0. And I know tangent is positive. Oops, first let me solve for the reference angle. That's 0 radians. Okay. Tangent of theta. So tangent of theta is positive in quadrants 1 and quadrant 3. So in quadrant 1, let's try to do this without drawing a Cartesian coordinate system. Our angle in standard position equals our reference angle, and that equals 0 radians. In quadrant 3, our angle in standard position equals pi plus our reference angle. So our angle in standard position in quadrant 3 equals pi radians. So let me circle pi radians and 0. This one, let's solve for tangent of theta. So tangent of theta equals 3. I have the reference angle equals the inverse tangent of the absolute value of 3. My reference angle, so I'm going to have to make a decimal here. 1.25 radians is my reference angle. Same as over here. Tangent of theta is positive, so I'm in quadrant 1, which gives me a reference angle, or an angle in standard position, equal to my reference angle, and that's equal to 1.25 radians. In quadrant 3, I'm going to have an angle in standard position equal to pi plus my reference angle, and that equals pi plus 1.25 radians. And as an approximate value, I have 4.39 radians. So I have actually 4 solutions here, folks. Solutions. 0, 1.25 radians, pi radians, and 4.39 radians. So when we make an error like this, where we divide out one of our solutions, the original solution had one solution, 1.25. Look what happens when you divide that out. We should have 4 solutions. Okay, so just be careful when you're doing that. Next page. Okay, determining the general solution for trig equations. So what happens if the domain restriction was removed? So all these examples that we did, including the startup, and then part 1, we had a restricted domain where we said it's like 0 to 2 pi, or 0 to 360 degrees, or negative pi to positive pi. What if we remove the restriction, right? So if we extend the domain infinitely, there will be infinitely many solutions to the equation. So writing the solutions over the domain, negative infinity to positive infinity, is called the general solution. To write a general solution, 2 things here. Determine the solutions to the equation for a single rotation of the unit circle that is within this domain, 0 to 360. Then add a full rotation an infinite number of times unless the solutions are symmetrically apart from one another. So symmetrically apart meaning 180 degrees apart. Okay, so I'll write this note. If angles are symmetrically apart, angle will vary by pi radians or 180 degrees. Okay, and you can see that when we do the cotangent and tangent solutions, because think about the period for cotangent and tangent. Well, the period's pi radians, so you're going to have solutions that are symmetrically apart, meaning pi radians, 180 degrees. And we'll show you what that looks like when we do the solutions. First, let's do a basic one. Determine the general solution, example 1, for each of the following in both degree measure and radian measure. So if I have sine of theta equals 1/2, so we'll do the general solutions for some basic problems. So first I need to find the reference angle. So I take the inverse sine of the absolute value of 1/2. And what's my reference angle for the inverse sine of 1/2? Well, the y value is 1/2. That is pi over 6 radians. Okay, so sine of theta is positive. So what quadrants am I in? Sine of theta is positive. Well, I'm in quadrant 1 and quadrant 2. So the solution in quadrant 1, we know that the angle in standard position is equal to the reference angle, and that's pi over 6. What about quadrant 2? We know that the angle in standard position is equal to pi radians minus the reference angle, and that equals pi radians minus pi over 6, and that equals 5 pi over 6 radians. Okay, pi over 6 and 5 pi over 6, do they differ by pi radians? Meaning, are they directly across symmetric, right? Do they divide that unit circle in half? Well, if I add 6 pi over 6, I get 7 pi over 6. So they're not the same, right? So we can stop here and then write a general solution like this. So general I should do this. We got the room to do it. So if I look at pi over 6, there's theta. And then where's 5 pi over 6? 5 pi over 6 is over here. Two solutions, right? So they're not pi radians apart. So what I can say is that when I'm writing my general solution, I can just add 2 pi over 6. So if I add, I can add 2 pi, which is 12 pi over 6. So if I start here and I add 2 pi, I'm going to go one rotation around. Well, that angle is pi over 6 plus 12 pi over 6, and that's 13 pi over 6. Likewise with this one, if I take this and go 2 pi around, another 2 pi, I will get 5 pi over 6 plus 12 pi over 6, and that's 17 pi over 6. I can keep going on and on in the positive direction, or I can go in the, and I can also go in the negative direction, right? So you have to write a general solution like this. general solution, um, theta equals pi over 6 plus 2 pi n, where n is an element of all integers, and then theta also equals 5 pi over 6 plus 2 pi n, where n is an element of all integers. So remember, integers, I can put in a -1, I can put in a 0, I can put in a 1, 2, 3, 4, 5, -1, -2, -3, on and on. Okay, so that's the general solution in radians. In degrees, what does that look like? Theta equals pi over 6 is 30 degrees, so 30 degrees plus 360 degrees n, where n is an element of all integers. And then theta equals, well, 5 pi over 6 is 150 degrees plus 360 degrees n, where n is an element of all integers. And there's our solution in degrees. Okay, letter B. Tangent of theta minus 1 equals 0. Okay, first off, let's solve for theta. Tangent of theta equals 1. Reference angle equals the inverse tangent of the absolute value of 1. So my reference angle equals pi over 4. Okay, from here, tangent of theta is greater than 0. It's positive, so I need to be in quadrant 1 or quadrant 3. So in quadrant 1, I know that angle in standard position equals the reference angle, and that equals pi over 4. In quadrant 3, my angle in standard position equals pi plus the reference angle, and so that equals pi plus pi over 4, and that equals 4 pi over 4 plus pi over 4, that's 5 pi over 4. Okay, here's my two specific solutions within a limited domain. How do I think about this in terms of an infinite domain? All right, let's map these two out. Pi over 4 and 5 pi over 4. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Okay, so there's theta equals 5 pi over 4. Well, are they 180 degrees out? Well, what if I take pi over 4 plus pi, which is the same thing as 4 pi over 4? I get 5 pi over 4. Okay, so, and that is actually our second solution. So if I do the same with 5 pi over 4, and I add 4 pi over 4, I get 9 pi over 4. Well, if I add 4 pi over 4 here, I get 9 pi over 4. So instead of varying this, instead of stating a general solution in terms of 2 pi, we need to vary this in terms of a single pi, 1 pi. So I'll show you what that means. Let me just clean this up. So our general solution theta equals pi over 4 plus pi n, where n is an element of all integers, and theta equals, do I need to say 5 pi over 4 plus pi n? No, because that's redundant. Because if I plug in a 1, that's pi over 4 plus pi, which is 5 pi over 4. So we don't need to state 5 pi over 4 and add pi over pi n to it. That's just redundant. Okay, so I can just simply list it as pi over n. What if instead, just be careful here, what if instead I did this, right? What if I said 2 pi n? Well, what happens? Let's see. Pi over 4 plus, let's say for n equals 1. That's 2 pi, which is 12 pi over 6. Oops, not. That's 8 pi over 4. And that equals 9 pi over 4. Okay, that's fine, but then I have to take my 5 pi over 4. And what if I add the same 8 pi over 4? Because now we're thinking that, hey, maybe the general solution is 2 pi n. Well, that's 13 pi over 4. Okay, now you have pi over 4, 5 pi over 4, 9 pi over 4, and 13 pi over 4, and you can keep going on and on and on. Well, the problem is that it's just super redundant, right? And it's a lot easier if we just vary it by pi and simplify the solution. So taking all of this out, we can just simply state this as our solution. Okay, so it's just a lot cleaner to show your work that way. In degrees, what does this look like? So in degrees, I have theta equals 45 degrees plus, not pi n, 180 degrees n, where n is an element of all integers. So there it is in degrees. Okay, next page, example 2. If 2 cosine squared of theta minus 1 equals 0, solve for theta in the domain 0 to 2 pi, give solutions as exact values. Okay, so this one, oops. Two cosine of theta equals 1. Cosine squared of theta equals 1/2. And then I take the square root of both sides. And I get the cosine of theta equals plus or minus 1 over square root of 2. And then if I rationalize this, plus or minus square root of 2 over 2. Okay, let's do the positive and the negative case. So I have cosine of theta equals positive square root of 2 over 2. My reference angle equals the inverse cosine of the absolute value of square root of 2 over 2. My reference angle equals pi over 4. Cosine is positive, so cosine of theta is greater than 0, so I'm in quadrant 1, I'm in quadrant 4. So in quadrant 1, my angle in standard position equals the reference angle, which is just pi over 4. So reference angle equals pi over 4. In quadrant, 4, not 3. So in quadrant 4, angle in standard position equals 2 pi minus my reference angle. So my angle in standard position equals 2 pi minus pi over 4. So my angle in standard position is 7 pi over 4. So I have one solution there, another solution there. How about the other case? Cosine of theta equals negative square root of 2 over 2. my reference angle equals the inverse cosine of the absolute value of negative square root of 2 over 2. My reference angle equals pi over 4. So cosine of theta, so my cosine ratio is this time less than 0. Where does that happen? That's in quadrant 2 and quadrant 3. So in quadrant 3, my angle in standard position equals pi radians minus the reference angle, and that equals pi radians minus pi over 4, and that equals 3 pi over 4. That's another solution. And then quadrant 4, angle in standard position equals, quadrant 3, sorry about that, quadrant 3, my angle in standard position equals pi plus my reference angle. So that equals pi plus pi over 4, and that equals 5 pi over 4. Okay, so off to the side, my solutions, they want exact solutions in the domain 0 to 2 pi. So my solutions are theta equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Part B. Determine the general solution for 2 cosine squared of theta minus 1. So the same equation that we're looking at, equals 0, where the domain is real numbers measured in radians. Okay, so in our domain, domain 0 to 2 pi, our solutions from above were pi over 4, theta equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. What's our general solution? So first of all, do any of these vary by pi over 4? So we need to be careful here. Sorry, do any of these solutions vary by pi radians, right? So are they symmetrical? So if I look at this solution and this solution, they differ by pi radians. And then likewise, this solution and this solution, they also differ by pi radians, right? Because I'm just going to take a look at this. Pi over 4 plus 4 pi over 4, that's 5 pi over 4. 3 pi over 4 plus 4 pi over 4, that's 7 pi over 4. So when we write the solution, let's write a general solution where we're not being redundant here. Okay, so let me just off to the side there. What's my general solution? If I take theta equals pi over 4 and I vary it by pi radians, and n is an element of all integers, that will get me this set right here, right? So it'll cover 2 of those. So I don't need to state 5 pi over 4 as a separate solution, as a separate general solution. So that part is nice and neat, and that I don't have to write too much here. And then I need to write 3 pi over 4 in terms of a general solution, which is pi n, where n is an element of all integers, and that takes care of this set. Okay, so this set was taken care of by the yellow one, so my general solutions are right there. So we don't need to write all four of them with 2 pi because I have cases where they differ by pi radians. So let's be more efficient there, okay? Example 3, the general solution to the equation square root of 3 cotangent of theta minus 1 equals 0 is, okay, so we got a cotangent. So I am wary or suspicious here because when you have tangent, you know that the period is pi radians, right? And cotangent, because it's the reciprocal of the tangent function, that also varies by pi radians. So I'm going to suspect that there's going to be a general solution that we need to shrink down and write it more efficiently. So let's solve this. So square root of 3 cotangent of theta minus 1 equals 0. Square root of 3 cotangent of theta equals 1. Cotangent of theta equals 1 over square root of 3. And let's see. So I'm going to solve this in terms of the tangent ratio. So 1 over the tangent of theta equals 1 over the square root of 3. Okay, so I'm using that reciprocal identity. And then when I take the reciprocal of both sides, I have tangent of theta over 1 equals square root of 3 over 1. And I can just write it simply like this. Tangent of theta equals square root of 3. Let's solve. The reference angle equals the inverse tangent of the absolute value of square root of 3. And so my reference angle is pi over 3. So I'm looking at this in terms of a tangent ratio. It's positive, greater than 0. So I know I'm in quadrant 1 or quadrant 3. So in quadrant 1, I know the angle in standard position is equal to the reference angle, so that's just pi over 3. In quadrant 3, I know that the angle in standard position equals pi plus the reference angle. So the angle in standard position is pi plus pi over 3, and that equals 4 pi over 3. So I have two solutions within a set domain, but I want a general solution. So one of the things I'll look at is if I take pi over 3 and I add pi, I'll get 4 pi over 3, which is that one. So I don't want to state this and this with pi n. I can just state one of them with pi n, and that will cover all of them, which is why we call it the general solution. Okay, so general solution. General solution. That's theta equals pi over 3 plus pi n, where n is an element of all integers. So which of these matches right here?